A bicycle rider rides up a hill. At the bottom of the hill, the rider has a kinetic energy of 200 joules and 0 potential energy. The rider does 700 joules of work while pedaling up the hill. At the top of the hill, the rider has 850 joules of potential energy. How much kinetic energy does the rider have at the top of the hill? I'm going to start by drawing an LOL diagram. I have information about kinetic and potential energy on each side. And the thing in the center here is my biker. So if we're going to place some bars on here, at the bottom of the hill, they have a kinetic energy of 200 and 0 potential. So I'm going to put an X here and I'll give kinetic energy a bar. We know that the rider does work, 700 joules of work. So I'm going to put this here. And remember, we show work going into the system like that. At the end, I'm wondering how much kinetic energy does it have? But I also know that I have a lot more potential energy. I have 850 joules on the right-hand side, whereas before I had none. I know I have kinetic energy because he's still pedaling, he's still moving at the top. We're just wondering, how much kinetic does he have? Using this that we've put on the bottom, we're going to create an equation. So EKI plus EPI plus work equals EKF plus EPF. So I use I and F for initial and final, or before and after, right? Top of the hill, bottom of the hill, all that stuff. So as I look here, I can plug in some values. So EKI, my initial kinetic energy is 200 joules. My initial potential energy is 0, so I don't need to include that, plus 700 joules of work is going to be equal to EKF, which is what I'm solving for, plus EPF, which I know is 850 joules. If I simplify a little bit here, I get 900 joules is equal to EKF plus 850 joules, which tells me that 50 joules is equal to EKF. So my final kinetic energy at the top of the hill is 50 joules.